Welcome to this coding problem walkthrough. In this session, we'll tackle problem number 40, combination sum 2. This is a popular problem that challenges us to find unique combinations of numbers that add up to a given target. We'll explore the brute force approach and discuss its intuition, along with its trade-offs. Let's dive in and solve this step by step. In this problem, you are tasked with finding all unique combinations of numbers from a given list, called candidates, that add up to a specified target value. However, unlike some similar problems, each number in the candidates list can only be used once in a combination. This means if a number is used in a combination, it cannot be reused elsewhere in the same result. The output should consist of a list of lists, where each inner list represents one unique combination of numbers that sums to the target. Additionally, the order of combinations in the output does not matter. For the input format, you're provided with a list of integers, candidates, where the list can have between 1 and 100 elements, and a target integer, which ranges from 1 to 30. The goal is to return all valid combinations in the described format. For example, if the input candidates are 10, 1, 2, 7, 6, 1, 5, and the target is 8, the output would be 1, 1, 6, 1, 2, 5, 1, 7, 2, 6. These are the only unique sets of numbers that sum to 8. Notice that 1, 7, and 7, 1 are treated as the same combination because the order of numbers in a combination does not matter. Duplicates in the output are not allowed, so combinations must be distinct even if they involve the same numbers in a different arrangement. Now, let's look at another example. If the candidates are 2, 5, 2, 1, 2, and the target is 5, the output would be 1, 2, 2, 5. Here, the two valid combinations are 1, 2, 2, and 5, as those are the only unique sets of numbers that sum to 5. Importantly, 2, 1, 2 is considered the same as 1, 2, 2, so it is not included as a separate combination. This highlights the importance of handling duplicates properly in the candidates list to ensure the output contains only unique combinations. In a simpler example, if the candidates are just 1 and the target is also 1, the output would be 1. The only possible combination here is the single number 1, since it matches the target value. This example illustrates that even when the input is minimal, the solution must correctly identify any valid combination that sums to the target. Finally, let's consider some constraints and edge cases. The size of the candidates list can range from 1 to 100, and each number in the list is a positive integer between 1 and 50. The target value is between 1 and 30. If no combination of numbers can sum to the target, such as when candidates are 2, 4, 6, and the target is 1, the output should be an empty list. If there's only one candidate and it equals the target, the output should include just that single candidate. For example, candidates equals 5, and target equals 5 would result in 5. Proper handling of duplicates is critical to ensure unique combinations, as shown in cases like candidates equals 2, 2, 2, and target equals 4, where the output should only include 2, 2. This careful attention to uniqueness ensures the solution meets the problem's requirements. To begin, let's consider the brute force approach. The intuition here is to generate all possible subsets of the candidates array. Once we have all subsets, we can filter out the ones whose sum matches the target. To ensure we only keep unique combinations, we use a set or similar data structure to eliminate duplicates. Now, while this might sound straightforward, the complexity is where this approach becomes impractical. Generating all subsets takes 2 to the power of n, where n is the length of the array. Additionally, checking the sum for each subset and removing duplicates adds even more computational overhead. This makes brute force infeasible for larger input sizes. Another major drawback is that this method doesn't take advantage of the fact that the input can be sorted or that we can prune unnecessary computations. As a result, while conceptually simple, brute force is not a scalable solution for this problem. Now, a much better approach is backtracking with pruning. Here, the intuition is to use a sorted version of the candidates array to systematically explore only the viable subsets while avoiding duplicates. First, we sort the candidates, which ensures that duplicate numbers are adjacent. This allows us to skip over consecutive duplicates during our exploration. Then, we use a recursive backtracking function to build combinations step by step. At each step, we can either include the current number or skip it. If the current sum exceeds the target, we stop the recursion early. This is pruning, which helps us avoid exploring paths that are guaranteed to fail. Valid combinations are added to the result list, ensuring that we only keep subsets that meet the criteria. While this approach is still exponential in the worst case, pruning drastically reduces the search space, making it much faster than brute force. The main challenges here are handling duplicates carefully and managing the recursive calls efficiently. The chosen strategy for this problem is backtracking with pruning. There are a few key observations that make this approach effective. First, the uniqueness requirement is handled by sorting the candidates. Sorting groups duplicate numbers together, which allows us to skip over consecutive duplicates without needing additional data structures. Second, pruning is a critical optimization. If the current sum exceeds the target, we can stop exploring further, saving significant computation time. Lastly, backtracking provides a natural way to explore all valid paths while maintaining the current combination and reverting changes as needed. This balance of exploration and pruning makes backtracking both efficient and manageable. Compared to alternatives, this approach stands out because it avoids the exponential overhead of brute force while keeping the implementation simpler and more intuitive than dynamic programming, which might involve more complex state management. Finally, let's discuss the trade-offs of using backtracking with pruning. On the plus side, this approach is efficient for moderate input sizes. It avoids generating duplicate combinations and takes full advantage of the sorted input to optimize the search process. However, the approach is still exponential in the worst case, as subset generation problems inherently involve exploring multiple combinations. It also requires additional space for the recursion stack. When we compare this to other methods, brute force is clearly infeasible for larger inputs due to its 2 to the power of n complexity. Dynamic programming, while potentially useful, is less intuitive for this problem because of the need to handle duplicates and enforce uniqueness constraints. Overall, backtracking with pruning strikes the right balance between simplicity and performance. It ensures correctness, eliminates redundant computations, and handles duplicates effectively, making it the most practical choice for solving the combination sum 2 problem. To solve the combination sum 2 problem, we need to find all unique combinations of integers from a given array that sum up to a specified target. Importantly, each number in the array can be used multiple times, but duplicate combinations should not appear in the results. The most efficient way to handle this is by using a backtracking approach. Backtracking allows us to explore all possible combinations systematically, while also giving us the ability to prune paths that cannot lead to valid solutions. The first step in our algorithm is to sort the input array. Sorting helps us in two key ways. It ensures that combinations are generated in a consistent, sorted order, which makes it easier to avoid duplicates, and it allows us to stop exploring further as soon as we know the remaining target cannot be reached. This sorting step is foundational for efficiency and correctness. Once the array is sorted, we need to prepare some data structures. First, we use a result list, called results, to store all valid combinations we find. Additionally, we maintain a temporary list, named current, to keep track of the combination we are currently building. The backtracking process itself is defined in a helper function, which we can call backtrack. This function takes two parameters: start, the index in the candidates array where we begin our exploration, and target, the remaining sum we are trying to achieve. Now, the function has two base cases. If the target reaches exactly 0, it means the current combination is valid, so we add it to our results list and stop exploring further down that path. On the other hand, if the target becomes less than 0, it means the current combination has exceeded the allowed sum, so we abandon that path immediately. These base cases ensure the algorithm remains efficient and only focuses on valid combinations. The heart of the algorithm lies in the recursive exploration process. Here, we iterate through the candidates array starting from the given start index. For each candidate, we add it to the current list, essentially making a choice to include it in the current combination. Then, we call the backtracking function recursively, passing the same index to allow reuse of the current candidate and updating the target by subtracting the value of the candidate. This recursive call explores all possibilities with the chosen element. After the recursive call completes, we undo the choice by removing the last element from current, which is the backtracking step. This ensures that we can explore other potential combinations starting from the next candidate. Once all possibilities have been explored, we return the results list containing all valid combinations. To ensure correctness and efficiency, there are some key insights to keep in mind. Sorting the input array and always starting subsequent recursive calls from the current index ensures that duplicate combinations are avoided. Additionally, by terminating the recursion early when the target becomes negative, we prevent unnecessary computations. Allowing the same index in recursive calls is what enables us to reuse elements as many times as needed. Backtracking itself is a critical part of the algorithm, as it enables us to explore all potential combinations while systematically undoing choices to avoid side effects on future paths. The two primary data structures used here are the results list, which stores all valid combinations, and the current list, which temporarily holds the combination being explored at any given time. These structures are foundational for efficiently managing the exploration process. In addition to the algorithm details, analyzing the complexity and considering edge cases is essential. The input array, referred to as candidates, is sorted for efficient processing and to handle duplicates effectively. The time complexity of the algorithm is 2 to the power of n in the worst case, where n is the size of the candidates array. This is because we explore all possible subsets of the array. The space complexity is n, primarily due to the recursion stack and the current list used to store temporary combinations. Several edge cases should also be considered. For instance, if the input array is empty, we simply return an empty list. If no valid combinations exist for the target, the result is also an empty list. For arrays with a single element, we need to check whether that element can repeatedly sum to the target. Finally, for large inputs, pruning invalid paths early ensures that the algorithm remains efficient and doesn't exceed memory or time limits. To better understand how the algorithm works, let's walk through an example. Suppose the input candidates array is 2, 3, 6, 7, and the target is 7. We start with an empty current list. First, we add 2 to current, making the target 5. We add 2 again, reducing the target to 3. Adding 2 once more brings the target to 1. If we try adding 2 again, the target becomes negative, so we backtrack by removing the last 2. Next, we try adding 3 to the combination 2, 2, which achieves the target of 0. This combination, 2, 2, 3, is added to results. After backtracking further, we explore using 3 directly, and then 6, but neither leads to new valid combinations. Finally, we use 7 directly, which matches the target and is added to results. The final output is 2, 2, 3, 7. This demonstrates how the algorithm systematically explores and backtracks to find all unique combinations. This implementation solves LeetCode problem number 40, combination sum2, using a backtracking approach. The function combination sum2 takes a list of integers candidates and an integer target as input. First, we sort the candidates list. Sorting allows us to handle duplicates efficiently by ensuring that duplicate numbers are adjacent, and it also enables early stopping when a number exceeds the remaining target. The backtrack function is a recursive helper function that explores all possible combinations. It takes 3 arguments. Start, the current index in the candidates list from which to explore. Target, the remaining value we need to achieve. Path, the current combination being built. Inside the backtrack function, if the target becomes 0, we append a copy of the current path to the result list since we found a valid combination. If not, we iterate through the candidates starting from start. For each candidate, we skip duplicates by checking if the current candidate is the same as the previous one, and if we are beyond the starting index. If the current candidate exceeds the target, we break out of the loop early, as no further candidates can contribute to a valid combination. Otherwise, we add the current candidate to the path, recursively call backtrack with the next index and the reduced target, and then backtrack by removing the last added element from the path. This process continues until all valid combinations are explored. Finally, we return the result list containing all unique combinations that sum to target. The solution ensures that duplicate combinations are avoided and is efficient due to the sorting and early stopping mechanisms. Here, we begin by importing the necessary packages and defining our solution class. The main method, combination sum2, takes an array of integers called candidates and a target sum. Our goal is to find all unique combinations of numbers in the array that add up to the target. To handle duplicates and make the search efficient, we first sort the array. Then, we call the backtrack helper method, which performs the core recursive logic. The backtrack method takes several parameters: the sorted candidates array, the remaining target, the starting index for iteration, the current combination being formed, and the result list where all valid combinations will be stored. Inside the backtrack method, we first check if the target has reached 0, meaning we've found a valid combination. In that case, we add a copy of the current combination to the result list and return to explore other possibilities. Next, we iterate over the candidates array starting from the given index. To avoid processing duplicate numbers, we check if the current candidate is the same as the previous one and skip it if necessary. We also implement a pruning condition. If the current candidate exceeds the target, we exit the loop early since no further combinations will be valid. If the candidate passes these checks, we include it in the current combination and recursively call backtrack with the updated target and the next index. Once the recursive call has been made for a candidate, we need to undo the choice to explore other possibilities. This is achieved by removing the last number added to the current combination, which is what we call backtracking. By removing the number at the end of the list, we effectively revert to the state before the current candidate was chosen. The loop then continues, allowing the algorithm to explore the remaining candidates at the same level of recursion. This systematic process ensures that all valid combinations are considered without repetition, thanks to the checks for duplicates and the sorted order of the array. Ultimately, the backtracking approach allows us to efficiently generate all unique combinations that meet the target sum, and these results are returned to the main method. This completes our Java implementation of the combination sum2 problem. In the problem combination sum2, the goal is to find all unique combinations of numbers from the given list, candidates, that add up to a specified target value. Each number can only be used once in a combination, and the solution must exclude duplicate combinations. To understand the approach, consider the first example. The input candidates are 10, 1, 2, 7, 6, 5, and the target is 8. The first step is to sort the candidates into 1, 2, 5, 6, 7, 10. Sorting is essential because it helps us manage duplicates and allows for early stopping when a candidate exceeds the target. We then use a backtracking method, starting with an empty path and the full target value. For instance, at the very first step, we add 1 to the path, reducing the target to 7, and recurse further. Then, we try adding 2, which reduces the target to 5, and so on. When the target becomes 0, we found a valid combination, such as 1, 2, 5. If adding a number causes the target to go negative, we stop exploring that path. This process ensures that we systematically explore all valid combinations, such as 1, 7, and 2, 6, while avoiding duplicates. The final result for this example is 1, 2, 5, 1, 7, 2, 6. In the second example, the candidates are 2, 5, 2, 1, 2, and the target is 5. We start by sorting the candidates into 1, 2, 2, 2, 5. Again, sorting plays a key role in handling duplicates and simplifying the process of backtracking. Starting with an empty path and a target of 5, we first add 1, reducing the target to 4, and then add 2, reducing it further to 2. When we add another 2, the target becomes 0, yielding the valid combination 1, 2, 2. At this point, we backtrack to explore other possibilities. When we consider adding 5 directly, it matches the target, giving us another valid combination, 5. The backtracking process ensures that we explore all potential combinations systematically while skipping duplicates to maintain uniqueness in the final result. For this example, the final output is 1, 2, 2, 5. In the third example, the candidates are 3, 1, 3, 5, 1, and the target is 8. After sorting, the candidates become 1, 1, 3, 3, 5. Starting with an empty path and the full target of 8, the first step is to add 1, reducing the target to 7. We then skip the second one to avoid duplicates and proceed by adding 3, reducing the target to 4. Adding another 3 at this stage brings the target to 1, which doesn't lead to a valid combination, so we backtrack. Next, we try adding 5 to the path, 1, reducing the target to 2, but this also doesn't yield a valid result. By systematically exploring all possibilities, we eventually find 2 unique combinations, 1, 3, 3, and 3, 5. This example highlights a few key insights. Sorting simplifies the process of avoiding duplicates and enables early stopping when candidates exceed the target. The backtracking approach ensures that all potential combinations are explored, and skipping duplicates guarantees that each combination in the result is unique. These principles form the foundation for solving this problem effectively. To analyze the time complexity of this solution, we start with the sorting step. The input array of candidates is sorted initially, and this operation takes n*log n, where n is the number of elements in the candidates array. Sorting is a necessary pre-processing step to enable efficient duplicate handling and pruning later in the algorithm. Next, the recursive backtracking is where the bulk of the computation happens. In the worst case, the algorithm may explore all possible subsets of the candidates array. Since the total number of subsets for an array of size n is 2 to the power of n, this gives us an exponential number of recursive calls. However, the algorithm includes optimizations such as pruning branches where the sum exceeds the target and skipping duplicate values, which significantly reduces the number of recursive calls in practice. Despite this, the worst-case scenario still involves exploring exponential subsets. Additionally, for every valid combination found, appending a copy of the current path to the result incurs a cost proportional to the size of the combination, k. Across all subsets, the total size of these paths is bounded by 2 to the power of n. Now, let's delve deeper into the effects of duplicate handling and pruning on the algorithm. By skipping duplicate candidates and terminating early when the current candidate exceeds the target, the number of recursive calls is reduced considerably. However, these optimizations do not change the fact that the worst-case time complexity remains exponential. In edge cases, like when all subsets are valid solutions, the backtracking still generates and processes an exponential number of subsets. Combining this with the sorting step, the overall time complexity is n*log n plus 2 to the power of n*k, where k is the average size of the combinations. This worst-case scenario can occur, for example, when the candidates array is filled with identical values, and the target is large enough to encompass all possible subsets. These constraints highlight the inherently exponential nature of the problem despite the optimizations. Turning to space complexity, let's first consider the auxiliary space used by the recursion stack. The maximum depth of the recursion corresponds to the number of elements in the candidates array, so this requires n space in the worst case. Additionally, sorting the candidates array may require n extra space, depending on the sorting algorithm used in Python. Another major contributor to space usage is the result list, which stores all unique combinations. In the worst case, the number of combinations is 2 to the power of n, and since each combination has an average size of k, the total space required for the result list is 2 to the power of n*k. Combining these factors, the overall space complexity is n plus 2 to the power of n times k. This means that both the recursion stack and the result storage play significant roles in determining the memory requirements of the solution. Now let's break down the time complexity further into best, average, and worst cases. In the best case scenario, the target is very small or no valid combinations exist, allowing the recursion to terminate early. Here, the time complexity is dominated by the sorting step, which is n*log n. In the average case, pruning and duplicate skipping reduce the number of recursive calls significantly, but the exponential nature of the subset generation keeps the complexity at 2 to the power of n*k. In the worst case, where all subsets are valid solutions, such as when the candidates array contains many duplicates or the target is very large, the algorithm must explore all 2 to the power of n subsets, leading to a time complexity of 2 to the power of n*k. Mathematically, sorting the array at n*log n and generating and processing subsets at 2 to the power of n*k combine to yield the overall time complexity. On the space side, recursion depth contributes n, while result storage adds 2 to the power of n*k, resulting in a total space complexity of n plus 2 to the power of n times k. This analysis underscores the balance between the inherent computational challenges of the problem and the optimizations introduced by the algorithm. When solving combination sum 2, there are several common mistakes to watch out for. One frequent issue is not handling duplicates properly. If the input contains duplicate numbers and you fail to account for them, your solution may generate redundant results. For example, with the array 2, 2, 3, and a target of 7, you might end up with multiple copies of the combination 2, 2, 3. To fix this, sort the input array and skip duplicate candidates during backtracking by checking if the current number is the same as the previous one after the first position. Another common pitfall is relying on brute force methods, such as generating all possible subsets and then filtering by the target. This approach has exponential time complexity, which becomes impractical for larger inputs. Instead, use backtracking or dynamic programming to narrow the search space more efficiently. Lastly, it's easy to overlook edge cases, such as an empty input array, no valid solutions, or repeated candidates that exceed the target. Always test these scenarios explicitly to ensure your solution is robust. Another frequent mistake is failing to prune the search space effectively. If the current running sum exceeds the target, there's no point in continuing down that path because it can't lead to a valid solution. To address this, implement pruning logic in your recursive function to terminate early when the sum goes beyond the target. Additionally, incorrect base cases in recursion can cause problems. For instance, forgetting to add valid combinations to the results or mishandling when to stop the recursion may lead to missing solutions. It's crucial to define clear base cases. Ensure that when you find a valid combination, it's added to the results, and that the recursion stops when no further exploration is needed. These fixes help make your backtracking algorithm both efficient and correct. Understanding key patterns and optimization techniques can make a big difference in solving problems like combination sum 2. Many problems involving subsets, combinations, or partitions are best approached using backtracking, so recognizing when this technique applies is essential. To optimize your solution, always sort the input. Sorting helps simplify duplicate handling and enables effective pruning by allowing you to terminate early when the current sum exceeds the target. For problems with overlapping subproblems, consider using memoization or dynamic programming to further improve efficiency. During interviews, it's also important to communicate your thought process clearly. Explain how you handle duplicates, edge cases, and pruning as you go through the solution. Finally, be prepared to discuss the scalability of your approach. For example, backtracking typically has exponential time complexity, 2 to the power of n, but you should also be able to compare it to dynamic programming approaches in terms of both time and space complexity. Combination sum 2 is closely related to other problems that you might encounter. For instance, combination sum, LeetCode 39, allows unlimited use of candidates, while combination sum 2 restricts each element to a single use and requires handling duplicates. Subset sum, LeetCode 416, asks whether a subset exists with a sum equal to the target, making it a decision problem rather than a combination generation problem. Permutations 2, LeetCode 47, involves generating all unique permutations of an array that contains duplicates, which also requires managing repeated elements. When considering alternative approaches, backtracking remains a strong choice due to its systematic exploration of possibilities, though it can be slow for large inputs. Dynamic programming is another option, particularly for problems with overlapping subproblems, as it can be more efficient but requires additional space and is sometimes harder to implement. Lastly, iterative subset generation is a simpler, non-recursive approach, but it may be less intuitive when handling constraints like duplicates or pruning the search space effectively. Great job following along. In this session, we reviewed the brute force approach to combination sum 2 and highlighted its strengths and weaknesses. Remember, while brute force can provide insights, it's essential to evaluate the trade-offs in time and space complexity. Thanks for tuning in, and make sure to subscribe for more problem-solving tutorials. Keep coding, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!